Okay, guys. As I said previously, I don't know if you noticed or not. I just post a note as the most recent updates on the Schoology website, which is talking about, I should say, one of your coming assignments, which is going to be about, I should say, which is due by next weekend, about the Hodgkin-Huxley model. This model is very advanced and it won the Nobel Prize in Physiology, which it describes the movements of the action potential along the neurons in the brain. This math is very advanced. I don't want you to reproduce the math because it's very advanced, but I just wanted you actually to do the research, for example, from the Wikipedia website, and to see how the knowledge of the mathematics and especially the functions can help you to describe some phenomenals in nature. And in one of the most complex cases is that you can model the function of the brain and how the brain and the neurons are working. And this is a very, I should say, interesting model. Please work on it, do the research. A qualitative research, you do not need to produce any math, but to know how it works. And you have to submit a paper which comprises 500 words at least, and submitted that to the Science Club as a blogging which you do. Depending on the quality of your work, it comes to maximum of 10% of your final mark, okay? And the deadline for that is gonna be by the next week, the midnight of the next Monday. You have 1 week. Please start working on it as soon as you can, because it's not an easy model. Then it requires lots of work. Okay, and now today we are gonna continue with some new stuff. But before we are gonna run a workshop. Any questions before I just move on? Any questions, guys?
No.
No? Okay, guys. Now, the thing which we're going to do is that today we are just going to spend 20 minutes on a kind of a workshop. And the workshop is that I just want each one of you, please go to your Desmos website and plot the tangent and cotangent function and try to observe if those functions are odd, even, and what is the periodic behavior of those functions. Okay? And then you share your screen with us to talk about your findings on the plot. Okay, you talk about the domain, you talk about the range, if the function is odd or if the function is even, and what is the periodic behavior of the function. Correct? For two functions, tangent and cotangent. Okay.
Okay.
Is everybody here? Say your name, guys, if you are there.
Rose.
Rose.
Philip.
Ferris.
And Ferris. And where is Gloria? She left right now then. Okay, guys, I think 15 minutes is good. Plot cotangent and tangent function, and to answer if those functions are even or odd, or what kind of behaviors they have. In 15 minutes, then we come back to share the results. And in the meantime, I turn my laptop upside down to start the session, the new session, which is going to be a very exciting day. Okay, I just prepared a lesson for today. Okay, guys, are you done?
Not yet.
Okay. Is it good 5 minutes? You come back then?
Yes.
Awesome. Also, we had a very important lesson today. It's gonna be the best lesson we ever have had. Then you want to start too early then. Okay. Guys, how's everyone doing? Doing great?
Yes. But I can't find the domain of the function.
No worries, no worries. You're gonna do that together. Let me share my window. And after that, we are gonna do something very exciting, guys. One of the exciting things ever. I'm gonna share my screen with you guys. Where is my Desmos? Everyone sees my screen now?
Yes.
Yeah, great. Oh, why my Desmos is like that? Oh. Why those grids shows up there? Okay. Okay. Oh, now much better. Okay, we have f of x what? F of x equals to, let's say, the tangent of the x. Guys, please hold on a second. Guys, please just write the conclusions that we are just going to derive from everything that we discuss, because you need that in future lessons then. Okay. Okay. Okay, what happened? Do you have my screen yet? Okay, it seems that I lost it. Okay. Guys, look at that. The first function that we are going to talk about is going to be the tangent of the x. You see the global picture of the function. You see that? It's all over the place. It means that this is periodic. Okay. Guys, what is the range of this function? What is the domain of this function? That's the first thing that we're going to talk about that. Hello?
Hello?
Guys, can you hear me?
No, we couldn't.
Yes.
How about now?
Yes.
Awesome. Guys, look at the range of the domain of this function. You see that, for example, it's from 0. You see these plots. We accept that the range can be any number. It's going to be the R. There is one trick that we're going to talk about that in future, but when I just get the, when I go back to my screen, I'm going to show that to you. I have to share my screen. Let's stop sharing. I want to show that something to you. Guys, can you see my paper?
Yes.
Yes, nice. Let's get it started. It's going to be the April 20th. April 20. Guys, when we talk about the function, and the function f of x is essentially the tangent of the x. And when we talk about the domain, what is your best guess for the domain of the function? I mean, the acceptable values of the x, and the function can be defined. Does it make sense if I say that's the domain of the function, domain of the tangent of the x? It's the set of x which belongs all to real number. Can I say that? But you may wonder to ask yourself, it can be any real number, but what is the nature of the tangent of the x, guys? Please listen to that. That is very important. What is the real nature of the tangent of the x? How do you know the tangent of the x? We talked about the tangent of the x. When we talked about the trigonometric function, guys, we said that the trigonometric functions essentially are 6 ratios: sine, cosine, tangent, cotangent, secant, and cosecant. Out of those 6 ratios, 2 of them are the building blocks, the sine and cosine, because you can build up other 4 ratios using those 2 building blocks. For example, the tangent of the x was what? How do you make the tangent of the x? You come to say sine of the x over cosine of the x, correct? That's what we learned, right?
Yes.
That's right. Then if you look at that, guys, the nature, the real face of the tangent of the function, just give me 1 second. It's getting a little bit hot here. I just want to open the window. I just come back in 2 seconds. Okay, now you will see that the tangent is the sine over cosine. But the problem is what? You remember it from the past that when we talked about the function, any type of the function, and when we said that, for example, f of x, I'm going to write it here. We said that, for example, f of x is a function which is, let's say, it is defined by g of x divided by h of x. That's a general type, the rational expression, the functions which they have. This is the rational expression, the functions which they have, the numerator and the denominator. And but when we talked about these functions, we said that there is a problem, and the problem is that h of x, the thing which is at the denominator, should never ever become 0 under any circumstances. That's right. Then as a result, for these type of functions, when we came to define the domain of the function, we said that the domain is going to be the x which belongs to the R. However, x should not belong to h of x becomes 0, which it means that you exclude the x that makes the denominator of your rational expression go to 0. That's right. That's how we defined, I should say, a rational expression, which is the ratio of two functions, and we said that the denominator should not become to 0. For example, as an example, I'm going to write it here. Everyone see this if I write here? As an example. Look at this function that f of x equals to what? For example, let's write a tangent of the x divided by x minus 2. Guys, everyone can see this function? The tangent of the x divided by x minus 2?
Yes.
If I want to find the domain of the function, what is the domain of this function? Let's not write the tangent of the x. That makes it simple. Let's write it the x over x minus 2.
X cannot be 2.
That's so true. We say that, okay, d becomes x belonging to the R. However, x should not be equal to 2, because if you put 2 there, it becomes a nasty looking function. The denominator of the function goes to 0, and that's the least thing that we expect, that the denominator of a function goes to 0. We have to always avoid it. How to avoid it? We have to exclude it from the domain of the function. Then if the domain can be any number, we have to exclude from it, remove from it, those numbers that makes the denominator of a function 0. That's right. And now go back to the same thing. We're looking for the domain of the tangent of the x. We have the same problem. Now the tangent of the x in reality is a function which is constructed by the division of two functions, a ratio of two functions, the sine and cosine. Okay, what is the domain of the function then? The domain can be any x which belongs to the real number, however, that the x should not belong to the fact that cosine of the x becomes 0. Because if cosine of the x becomes 0, oh my God, you end up with a very nasty looking function, which its denominator is 0. So far, so good, everyone?
Yes.
Yes, Gloria, Faris, Philip?
Yes.
Awesome. And now, where this can happen? That the cosine of a ratio becomes 0. And now that's the thing that we have to discuss about that. Where the cosine of a function becomes 0.
When x equal to 90.
When x what?
When x is 90 degrees.
That's so true. Thanks, Rose. When x is 90 degrees. I'm just plotting this one. It's the Cartesian coordinate y. This is gonna be the x. It's gonna be the 0 there. And now the thing which you will see is that that's a unit circle, as the thing which you always did. And I'm gonna define my angle like this. And I say the angle is a typical angle which I have, which its cosine, it's actually the projection along the y on the x coordinates. If the angle is alpha, let's call the angle x. Oh, I wish if I had called it alpha. Let's call that x dot to exclude it from the x. Look at this one, guys. The definition of the cosine, what is that? We talked that the cosine of the x equals to what? whatever you read along the x coordinate, which is going to be this, that's right, divided by r, the radius, correct? Then we say that because the radius is 1, then the cosine is going to be x itself. So far, so good, everyone?
Yes.
But where the cosine of the x becomes 0, there the x, which is the projection of this point, I call that A, becomes 0. There should be no projection. Where these spots happens, one of them is, Rose said that one of these places that the x becomes 0 is at this point. It means that the angle starts from here, moves all the way back there to, let's say, along the y-axis, which the angle is what? Pi over 2 in radians, or 90 degrees. At this point, you see that the cosine of pi over 2 becomes how much? Becomes 0. On the other hand, how about this point? Three pi over 2. Is it correct? Can I say that at this point also, the cosine of the x's becomes 0? That's right. Can I say that?
Yes.
Nice. Then can I just also, when I just make the full rotation to 2 pi, can I still move on to the next point? Again, I said it's going to be 2 pi plus pi over 2. Again, the cosine is 0. Because you know that the unit circle, you can rotate infinitely around the circle. Then when you come back here, you say that, okay, it's going to be 3 pi divided by 2 plus 2 pi. Again, the cosine becomes 0. Can we say that?
Yes.
That's right. Then as a result, when you have the function that the cosine of the x equals to 0, then it means that x equals to, we had pi over 2, 3 pi over 2, 5 pi over 2 becomes, as a general formula, becomes 2n plus 1 divided by 2 multiplied to the 2 pi. Correct? Any questions, guys?
No.
Rose, you said
No
no.
question.
Gloria, Ferris?
No.
No? Okay. If that's the case, then when you want to talk about the domain of the tangent of the x, if the function is tangent of the x, then you say that the domain of that function, it's going to be the x belonging to the all real numbers. However, x cannot be 2n plus 1 divided by 2 times p. Guys, n here is any real number. N, when I mention n can be 0, can be plus minus 1, plus minus 2, and go on. If n is 0, the first x, which the cosine becomes 0, becomes pi over 2. If you put n equal to 1, becomes 3 over 2 times pi. If you put n equal to 2, becomes 5 divided by 2 times pi. That's right. That's what n means. Pi is a constant, 3.14, but n is 0 or 1 or 2 or 3. If you are rotating counterclockwise, then you pick up these values to pick up these values to make your cosine to be 0. Then the domain of this function then becomes this, the tangent of the x. Then becomes any real number but the real number is in a way that the x should not be 2n plus 1 divided by 2 times pi, which n is any number, any real number, natural number, including 0. Then that's the domain of this function. Then x can be anything for tangent of the x, except that x should not be these ones, because it makes the denominator of the tangent, which is cosine of the x, goes to 0. That's right.
Yes.
And also the range, as you notice it from the plot, the range can be any number. There is no limit. Guys, I have a question for you. Any questions, guys?
No.
Any questions? Any confusion? Any ambiguity? Any need for clarification? Rose, Philip, Gloria, Ferris?
Yes.
Questions?
No.
Philip and Ferris? Ferris and Philip?
Let me think. Wait a minute.
Guys, remember, if you do not ask questions, I get back to you with a question of my own. Remember, that's the trick.
No, I think.
How about Philip?
Yes.
No questions, Philip?
No question.
You're fine? Okay. If you have no questions, guys, we are moving on. Before we go to the cotangent function, I want you then, based on the things which you learned about how did I do to find the domain of the tangent function, I want you please to come here and find the domain of this function. I call that the function f of x equals to the tangent of the x. What is the domain of this function and the range? Is it good to have 5 minutes to work on it?
Is it cotangent?
That's
X.
right. Cotangent of the x. We work on the tangent, now we work on the cotangent. I think 3 minutes should be fine.
Paris，你放歌呢？
Sorry, guys, I just had a disconnection to the net. Okay, are you done?
Yes.
Awesome. What is the domain, Rose?
Pi. It cannot be pi.
It cannot be pi. That's right. That's great. That's great. Fantastic. Thank you. How about the others? Guys, you know that the f of x, if this is cotangent, it's essentially based on the ratios that you learn. It's nothing, just a simple ratio, which is going to be the cosine of the x over sine of the x. That's right. And now that's the real function that you have to decide what is going to be the range, what is going to be the domain. The cotangent is this ratio, the cosine divided by the sine. Then you come to yourself, you say, I see the function in front of myself, which is, I'm going to just find the ratio, the domain is a rational expression. It has a denominator. And it tells you that the denominator should not go to 0. But at what values the sine of the x goes to 0? That's the question that I'm just going to answer it now. In order to answer, as usual, we draw unit circle, the same things which we have done. I'm just going to show an angle. The angle is going to be called, let's say, alpha. And you know the sine of that angle is going to be the projection along the y. Then whatever you read from here, y, it becomes the sine of your angle, correct? That's what we learned before. Y, x, and that's it. Okay, guys, as you will see, the value of the y in this unit circle decides on your sine based on the definition, because we defined previously that the sine of the alpha, it's the value which you read as the y. For example, if the point A is here, and you see the point A with respect to the Cartesian coordinates, you see that it reads y. Then you have the y divided by the r. Then at the same time, because the radius of this circle is 1 unit, then it means that you are dividing y over 1, which becomes what? Y. Then at which points the value of the y is 0? At any points along the x coordinates. Am I right? If the point is on the x, in these 2 points, the value becomes 0 of the sine. One of them is what? 0 in terms of the radians, 0 radians. The other one is what? Pi radians. Am I right?
Yes.
How about the other point? I can just make from here, I can just come here, becomes pi. I can come here again. Any half circle, if I rotate any half circle, I get to this point. These 2 points, which is marked by cross, these 2 points give me the value of the sine equal to 0. Regardless of how many times I rotate around the circle, if I end up at these points, I get the value of the sine equal to 0. One of them is 0, one of them is pi. I can come here, 0, pi, then I get back to 2 pi, then I get to 3 pi. Any half circle is how many radians? Any half circles is pi radians, correct? Then any half circle you pave, it becomes the sine 0. 0, pi, 2 pi, 3 pi, 4 pi, 6 pi, 7 pi, 8 pi. You see that? Which it means that then if the sine of x goes to 0, it means that the x is equals to n times pi, which n can be 0, can be plus or minus 1, plus or minus 2, and it goes to infinity. Plus is for the time that you rotate counterclockwise, minus is the time that you rotate clockwise. Make sense, guys?
Yes.
So far, so good?
Yes.
Awesome. Then if I want to find the domain of the cotangent, then I say, okay, the domain of this cotangent function is going to be what? The domain of the cotangent function is going to be x can be any real number. However, x cannot be n times pi. Because if this is n pi, then n can be 0 or plus or minus 1, plus or minus 2, anything to infinity, then the sign of the x, which is at the denominator, becomes 0. And as a result, the function looks nasty, bad. Then we exclude them from the whole real numbers, and we say, okay, now that's the defeated domain for this function. Right? Any questions, guys?
No.
How about Ferris, Philip, and Gloria?
No.
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 Okay. Awesome. And how about the domain? How about the range of the cotangent function, guys?
All real number.
That's so true. All real numbers are the domain. Okay, what else then? What else we need to talk before we move on to the next topic? Okay, now let's discuss about the evenness and the oddness of these functions, then we move on. But before that, guys, we talked about yesterday also, oh, not yesterday, yesterday was Saturday. We talked about that on Friday. We said that besides the sine and cosine and the tangent and cotangent, we described two other ratios. One of them was secant of x, which it was essentially what? Was 1 over what? Anybody remembers?
1 over cosine x.
That's so true, 1 over cosine of the x. And also, we had another ratio. It was cosecant of the x, which it was what? Which it was 1 over sine of the x. Okay, before we move on, I just want to ask you, please, also take 2 minutes to find the domain of these two functions. You should know that by hand, right? By heart now, right now, because guys, it's a beautiful day, huh?
Yes.
Guys, are you done now? For the secant of the x, the domain is very simple. X belonging to the all real number. However, cosine of the x should not be 0, because if you look at that, cosine is at the denominator of the function, and because of that, you cannot have it 0. Which values gives you cosine of the x equal to 0? You got it when we talked about the tangent of the x. Remember?
Yes.
Which x should not be equal to 2n plus 1 divided by 2 times pi. Which n can be 0, can be plus or minus 1, can be plus or minus 2. It goes on to infinity. Plus is for the time that the angle which you are selecting is counterclockwise, and minus is for the time that the angle is rotating clockwise. Any questions on this, guys?
No.
No. How about Philip Ferris Gloria?
No.
Awesome. For this one, we solved it a couple of seconds ago. The sign is at the denominator. Then the domain can be any real number. However, x should not be chosen in such a way that it makes your sine x, which is at the denominator, goes to 0. Because again, if that happens, it becomes too nasty. Okay, when x goes to 0 at the sine x,
Okay, pi.
huh?
Pi.
Say what?
Pi. And pi.
That's so true. Which again, in this case, I don't know what's the problem today with my connection. It just kicks me out. Are you still there?
Yes.
Awesome, awesome. Guys, any questions so far then?
No.
About how to find the domain of tangent, cotangent, and secant and cosecant function. Everyone is doing great?
Yes.
Okay. Guys, before we go to the break, I have to show you the very last thing to You have my screen shared? Okay, you see my screen?
Yes.
Okay. Guys, before we go for the break, I'm just gonna take notice of two very important facts. We are not gonna talk about the periodicity or the periodic behavior of this tangent function. Look at this function, guys. You see that if I zoom out, you see a pattern of the curves which repeats all over. You see that? For example, it's as if you stand in front of the two parallel mirrors. Have you done that?
Yes.
What did you see, Rose, when you did that?
It's repeat in the mirror.
That's right. You see maybe 1,000 rows, huh?
Yes.
Or more. And that becomes like that. The function repeats itself. And in order to see at what instance it repeats itself, look at that. For example, I have a curve right now here. You see that at pi and p and 0. You see this point, guys?
Yes.
And if I move forwards at point 0 and pi, I have the same curve. It means this is the same rows. And if I come to 2 pi over 0, there is another curve which is exactly like the two previous curves. At 3 pi 0, the same curve. 4 pi 0, the same. 5 pi, the same. You see the pattern is repeating all over. It seems that at every pi, and the same thing back at minus 2 pi, at minus pi, minus 2 pi, minus 3 pi, minus 4 pi, minus 5 pi. Guys, you will see that? You see that at every constant pi, if there is a distance between two curves is pi, then the function repeats itself. Then that's why we call that the function has a period of pi. What does it mean? It means that the function repeats itself exactly at a distance of pi from the previous one. It means that if at this point, which is pi 0, Rose is standing there, if you take a distance of pi at this point, at 2 pi 0, you see another Rose. You walk for one more pi, when you get pi plus 2 pi becomes 3 pi, you see another Rose. And the same thing. And Rose is going to be infinite number of the times repeating itself. Any questions, guys?
No.
Everyone got the concepts of the periodic behavior?
Yes.
It means that when you find a period of a function, you can say for sure that the function is going to repeat itself deterministically, and for sure it's going to happen the same thing at, let's say, pi away from the original point. Any questions, Philip, Ferris, and Gloria?
No.
No.
Everyone is good?
Yes.
How about Ferris?
I'm good.
Awesome. And guys, this one is a cotangent of the x. The red one is tangent. The blue one is a cotangent. That we talked about the domain of that function. And now you see that every blue line, it's a curve. If I zoom out, oh my God, you see? It's all over the screen. It's like standing in the middle of the mirror. You see that again, if this point is pi over 2, the other one is 3 pi over 2. What is the difference, guys, between 3 pi over 2 and pi over 2? Can you subtract them, 3 pi over 2 and pi over 2?
Pi.
That's so true, that's pi. Then you will see that if the distance between each curve is pi, like the tangent, then the cotangent is also repeating itself. From pi over 2, 3 pi over 2, 5 pi over 2, 11 pi over 2, you see that these points, even at the minus side, which it means that your angle is clockwise chosen, you will see that these plots are repeated. Then it means what? You can start with one rows. For example, you can start with one Philip or one Gloria or one Ferris, and know that at every pi distance from them, there is another Gloria. And you say, okay, I'm sure what's going to happen at, for example, 13 pi over 2, I'm sure that the function is repeating itself. You see that?
Yes.
And that's what we call the periodic behavior. Any questions, guys?
No.
No? Okay, and how about Gloria? How about
No.
Philip? And Ferris? Philip and Ferris.
No.
No.
Okay, guys, I think that's the right time to take a break. 12:15 is right now. Please come back sharp by 12:30. We have a very important lesson to start with. That's going to be very important. Please be sharp back by 12:30 then. Guys, see you soon then. Hello, everyone. Are you back?
Yes.
Great. Fantastic. Fantastic. Let me just put the laptop upside down. Then we just move on. This is going to be the page number 4. And it's going to be page number 3. And I also have another page, which is going to be page number 1. No, it's going to be page number 1. Yeah. Okay. Okay. Now, now we just want to, from this stage, guys, we're going to talk about a kind of sinusoidal functions to just use the sine function that to also model some phenomenal in nature. Then. But before we do that, I just need to talk about some kind of transformations. I didn't teach you the transformations before because I saved it here as we just reached 2 stages that we need to work with them. It makes more sense to learn about them and to talk about them. Okay, now imagine that you have, I'm gonna draw 3 functions. One is gonna be this line, one is gonna be this line, and one is gonna be this line. These are gonna be my Cartesian coordinates, which I'm drawing in order to plot the function. Then we plot these functions, we are gonna work with them more, and this is gonna be my y, this is gonna be my x, this is gonna be y, this is gonna be x, this is gonna be y, this is gonna be x. Everyone sees these graphs, huh? These Cartesian coordinates. Okay, I'm just gonna start from the left, and I'm just gonna plot something. And the function which I'm just gonna plot is gonna be this one, which we have worked with that a lot in the past. And this function is gonna be y equals to x squared. Do you see this color, guys, or no?
Yes.
You see that?
Yes.
This is gonna be this function. In order to plot this function, what I'm gonna do is that, you know, this function is plotted very easily. It's a parabola, huh? That's right. This function y equals to x squared is a parabola. And that's defined by this. Okay, and now, look at this. I'm just gonna transform. We call these ones transformations. I need more space. Sorry, I have to just plot it down there. I needed more space. Not this one. I'm going to transform my function based on this. I say that I'm going to transform x to minus, let's say, I'm going to transform to the x minus, let's say, 2, for example. Okay, if I just, guys, what do I mean by this? I mean that if I accept that I have this function, look at this function. What is my original function? My original function is what? F of x, it's equal to what? X squared. Am I right? Then I just say to you that make this transformation in a sense that put x, transform it to the x minus 2. What it becomes? It becomes, and it means that whenever you see from these functions which I had on top, I come here, I say that f, instead of the x, I put what? X minus 2. And I continue becomes equals to x squared, but instead of the x, I put x minus 2x squared, right? I can call f of x minus 2 as a new function. I call that g of x. Then g of x becomes what? X minus 2 squared. You saw what happens there?
Yes.
That's right. But the only thing which was important was that you notice that I just made the transformations for the x with minus something. Then if I know the plot of the x squared, what's going to happen to the plot of this x minus 2 squared? I say if I'm going to plot x squared with dotted lines. You see these dotted lines?
Yes.
If this is going to be x squared, then x minus 2 squared is that if this is minus, then you have to say, okay, I go to the opposite direction, plus 2. Then at plus 2, you reverse, you just draw x squared. You see what happens?
Yes.
Which it means that if you are transferring along the x with something, let's say, for example, minus, you walk to the positive direction. And you may ask yourself that, okay, what happens if I make a transformation that x goes to plus x plus 2? What's going to happen? Then you say that you are going to create a function. I call that g of x becomes x plus 2 squared. On all starting from the x equal x, y equals to x squared. If that's going to be the case, then if this is positive, I say, okay, I could just come to the minus 2 here. Then draw x squared. You see this transformation? Then it means that, guys, you start. Let me recap. What did I say to you? Okay. Guys, look, what do I mean by these ones? I say that if you want to make a transformation, for example, you start with a typical function, which is a quadratic function, which is y equals to x squared. Then you can transform the function along the x. You move the functions along the x. You say that, okay, I just want to take my functions from the 0, push it towards the right by 2 meters. Then you say that, okay, the function has to be x minus 2x squared. Or you want to push the functions towards the minus direction. Then you say that it becomes x plus 2x squared. Then it means that you transform your x horizontally, then you move your graph on the x-axis. Then as a result, I'm going to say, please guys, listen to this very carefully. I'm just going to call the heading for that horizontal transformation. What do I mean by the horizontal transformation? I mean that I am moving my function along the x. The function f of x. The first thing is that if you make a transformation like that, x, you transform that to the x plus a. A can be any positive number. Then it means that the function, what happens to that? It means that the graph of f of x moves by a to the left. And that's what we did. We made x plus 2, then the plot was moved to the left by 2. Yes? Any questions, guys, on this?
No.
And now, as a very last part, because we are going to use this transformation a little bit later, we said that if we just make the transformation that x goes to, you transform the x to the x minus a. Now this is the minus. What do we mean by this transformation? This transformation makes the graph of the function, graph of f of x, moves by a to the right. Because you are just making that transformation towards the right. And like this one, the function was x squared. You transform the function x to x minus 2, then the function moves by 2 meters towards the right from the origin. We are going to work with this one more when we talk about the trigonometric function, but I just wanted to just have this concept first, that we can just talk about the horizontal transformation of a function. Any questions, guys?
No.
How about Gloria, Ferris, and Philip?
No.
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 Okay, let's do one example. Okay. Okay, now this is good. We talked about the transformation. We are going to do something very interesting as a very last thing for today. Then we continue more in depth with that tomorrow. I'm just going to talk about one scenario, guys. I'm just going to define a function, and I'm just going to call my function. Let me just put an example here. I'm going to define this function as p of x. P because it stands for population. I'm going to p of x equals to 1200 times, let me write it with different color, cosine of 5 pi divided by 10 times t plus 9,000. Okay. And now, guys, this function is gonna model the population of one bacteria. Okay. Now, we do not need to know about the details of that one, but we are gonna use these trigonometric functions to answer 3 things. The first thing is that the first question we are gonna answer is this: find the period of the function. then the thing which we're going to do is that let's do one by one. Let's do one by one. Okay. The first thing is that, guys, we're going to use the plots, first of all, to see the period. Please, everyone individually, just go to your Desmos, try to plot this on Desmos to see if you can find a period based on a graph. Then I come back and I show you how to do that analytically. Okay, guys, sorry, just when you plot it, it becomes very nasty. Let's put that by pi over 5. Sorry, I had to make a change. Pi over 5. Guys, are you done? Hello?
Not yet.
Oh, okay. What time is it now? It's 15. Okay, guys, I do that analytically. Then please, you just do that graphically. Then we see what happens then, because we have two tasks to perform for this function. Guys, when we want to find the period of a function, if you remember previously, we said what? We said that if f of x is a cosine of x, what was the period of this function?
Pi.
Oh, it was 2 pi. Do you remember that? It was the first plot that we just made. Then we say that essentially the t of cosine x, by the t I means the period of that function, was 2 pi. Let me share my screen with you guys and show that to you before we move on. Let me share my screen. Okay. Let's share the screen. Okay, and now let me do this. Let me call that h of x equals to cosine of x. Let me unplug this. Let me zoom this. Guys, for this one, look at that. You start from, let's say, for example, this one. These 2 points. These 2 points are the best ones. You see, for the cosine function, guys, we talked about that a couple of days ago, but not much in details. We said that. Everybody is there, please say your name if you are there.
Rose.
Philip.
Rest.
How about Gloria?
Iris.
Yes.
Okay. Guys, look at this one. In order to answer that question, that what is the period of that functions? Look at that. For the tangent function, it was very easy to see that. We saw that for the tangent function, every curve which is like the S, when it gets repeated after each pi radians, we said that it becomes the period of that function. Right? You remember it? But for the cosine of the function, it seems that it's a little bit different because we see that the function is continuous everywhere along the x. And we do not see one plot is repeated all over the x-axis to find the distance between them, then conclude that the period should be that much. That's right? That's the problem. And now, what do we do then? Guys, look at this one. Imagine that. Look at these 2 points. Look, imagine that I have also this one. Have you ever gone mountain climbing?
Yes.
Yes. For example, look at this very top bottom, which is the maximum value of the cosine function, which is 1 on the y-axis. Imagine that if Rose is standing at this point, and again Rose is there, at each top of the mountain, we assume that Rose is going to be repeated. Rose is here, Rose again as the mountain, Rose again at the top of the mountain once other more. Then you see that what is the difference, the distance between this mountain on the very top and this mountain on the very top?
2 pi.
2 pi, that's right, because we get the distance between, let's say, the difference between they have on the x-axis. This is 2 pi on the x, and this is 0 on the x. The difference is 2 pi. Then the distance between the two closest top of the mountain defines the period. Look at these two closest one. This is 2 pi, this is 4 pi. What is the difference? Two pi, huh?
Yes.
And how about these ones? The lowest part of the mountain. For example, look at that. This is pi. This is 3 pi. What is the difference?
2 pi.
2 pi. Then as a result, we say that the period of the cosine function and also sine function, the same thing, you can try it yourself, is always 2 pi radians. It means that if, for example, Philip is standing at one hill on the top of the mountain, again, you can find Philip at this point. And if Philip is there, you can find him again at this point. Philip is going to be repeated continuously at the top of every mountain. This provided that the distance between the top of each mountain is going to be 2 pi radians. Yes, Philip?
Yes.
Awesome. Then guys, remember, then from now on, we said that also we can just define the same thing for the h. Let me call that z of x. Let me call that z of x equals to sine of the x. look at for the sine of the same thing. If, for example, Ferris is at the top of this mountain, the next closest mountain is what? 5 pi over 2. What is the distance between these 2 points? 5 pi over 2 minus 5 pi over 2. 2 pi, huh? For example, look at these 2 points. 3 pi over 2, and the closest down of the mountain, 7 pi over 2. Again, the difference between these points and that point, again, is a 2 pi radians. Okay, then we look at it like that. Let's have all the plots here. Let's see how crazy it gets. Okay, now then as a result, we saw that for the cosine function, the period, which I showed that by the t, is going to be 2 pi. The argument was 1x cosine of the x, the period was 2 pi. But look at this function here. This function has cosine of the pi divided by 5t. Let me write this like that. I'm just going to talk about that. Guys, when you want to find the periodic behavior of one trigonometric function, you always look inside the periodic function itself, nowhere else. You take a look of what's happening inside the belly of this trigonometric function. What is inside of the cosine 5 pi t? Imagine I write it as the cosine of 5 pi divided by the x. It doesn't matter if this is x or t. For this function, what is the period? I say that for the cosine x, the period was 2 pi. And you can show that the period t of cosine of the pi divided by 5 times x should equal to the maximum period that can happen for the cosine. You look at the cosine function as a typical cosine function which has a period of 2. Then we say that for the cosine of the pi divided by 5 of the x, the period is gonna be the period of the cosine functions, which is 2 pi, divided by the coefficients of the x of the other function, which is what? Which is pi divided by 5. If this you multiply that, you get that it's going to be 10 pi divided by pi, which it takes you to the 10. And that's how you find the periodic behavior of any trigonometric function, provided you know the periodic functions of the sine x, cosine x, tangent x, and cotangent x. Then you divide it by the coefficients of the other function to get the period. Let me write the basic thing that we know. Imagine that if the function f of x is cosine of, let's say, a of x. A is a coefficient. Can you see this, guys? You see the color? Yes? Hello?
Yes. Yes.
You see the color, huh?
Yes.
If this is a coefficient, which is not 0, then you say the period, which I showed it by the t of cosine ax, it's essentially 2 pi divided by a. The same thing happens for the sine of the x, because the sine and cosine both have the same period. However, you can write it like that to say that if g of x, it's going to be the tangent of a of x. Now this is the tangent with the coefficient. Then we say that the period of the tangent of ax, a is a coefficient which is not 0, equals to how much? What is the period of the tangent of the x?
Pi.
Pi, then divided by the coefficient of the new function, which is going to be the a. Right?
Yes.
Okay. Now, then as a result, if I go back to the same problem, if this model represented, for example, the population of, let's say, a society or let's say anything, and if I get the period to be 10, it means that after every 10 years, the population fluctuates and goes back to its original value then. That's right. That's how we define the periodic behavior of the trigonometric function. But no worries about that if you got confused, because we have to work more on this. At the time, it seems that it's almost 1:05. Tomorrow, when we just meet, we continue working with these functions, but in more meaningful way then. Then we continue with the concepts of the periodic behavior of the trigonometric function. I'm just going to post some homework definitely for today that it's going to be due for tomorrow. But in the meantime, remember that, guys, to do your homework, then I would see you, I should say, on tomorrow. But before we leave, do you have questions?
No.
No? How about Gloria, Ferris, and Philip?
No.
No? If you have no questions, guys, I'm going to post a homework today for you, and tomorrow we continue with the rest of that concepts, modeling with the sine function then. If you have no questions, then I see you all tomorrow. Then have a nice day. Bye, everyone.
Goodbye.
Goodbye.